In this video we are going to prove the Moivre's theorem by induction. So here's how it starts. You start with the statement, I like to call it proposition n, which means just this is the statement we're trying to prove, the statement or proposition. So proposition n is that if you ever have cos theta plus I sine theta to the power of n, well, the n comes in front. That's what the theorem says, that's what the theorem proves, and we're going to prove that right now. So this is a big step again, that the n in the power can come down in front in the cos and sine. So you start off, so we do this by induction, and induction means we knock the first domino first, as it were. So we say, what's proposition 1? And proposition 1 means simply put in 1 instead of n on both sides. So you get cos plus I sine theta to the power of 1, and you get cos 1 theta plus I sine 1 theta on this side. And that's clearly true. I mean, both sides are now the same. So we tick off to say that that's proved. Proposition 1 is true. Then we move on to pk, proposition k, and k stands for, if we think of it as a line of dominoes from 1 to n, we've knocked the first domino. Now we're picking a random domino k in the chain, so we'll just stick with that one. And we're saying, okay, we're going to say that cos, it's just basically replacing the n with k. The n in the first line with k here. So we're saying the cos theta plus I sine theta to the power of k is cos k theta plus I sine k theta. And what we're going to do is we're actually going to assume that. We're not entitled to say that's true yet, but we will assume it just to see how far we get with this assumption. Okay, now the next step is always go from domino k to domino k plus 1. So proposition k plus 1. If you replace k with k plus 1 everywhere, so in the power on this side, and the k becomes k plus 1 on this side. Now, is that true? This is a question mark at the moment. We haven't proved this yet, so we're trying to see if this is true. And the technique is, I would label this the left-hand side, LHS, and this is the right-hand side. And starting off with the left-hand side, I would take this part here, cos theta plus I sine theta to the power of k plus 1. And I would basically split it up. There's a rule in your tables for powers, and the rule says if you have a to the power of p plus q, well, you can simply split the powers as a to the power of p multiplied by a to the power of q. So it's kind of that rule in reverse. If you got a power here plus 1, you can split the powers, and you can say that that's it's all that to the power of k multiplied by all that to the power of 1. So again, go to your tables and your rules of indices, and you'll see that rule written right there. It's obviously, it might make more sense backwards. If you use something to the power of k, for example, in the tables it says if I have a to the power of p multiplied by a to the power of q, well, the answer is a to the power of p plus q. So it actually might make more sense backwards if you're finding that step difficult. Okay, now the next thing is, with induction, you're always trying to kind of force pk into pk plus 1. So if we take this part right here, we'll notice that this is the exact, I've underlined in green, this matches up with pk. So pk is this, and these are equal, and so all three are now equal, which means we can replace this here with this on the right hand side. And that's what we do. So we pull this bit down in here instead of that. And the rest of it is really brute force, I suppose, just multiplying out the brackets the long way. There's no shortcut here. So we've got two brackets now, and everything in every term in this bracket is multiplied by every term in this bracket. So it's cos k theta by cos theta by I sine theta. Keep the I out in front. It's just neater to have the I highlighted there in front. Then it's this by this, again keeping the I in front, so it's sine k theta cos theta, and then it's this by this. Now that's I by I, which is I squared. And you've got sine k theta by sine theta. Of course, I squared is minus 1 in complex numbers. At this stage, we'll highlight what are the real parts and imaginary parts, because in complex numbers you always keep the reals together and keep the imaginaries together. So this part is real, this part is imaginary because it's got an I in it. This part is imaginary, it's got an I right there. Now this part has become real because I squared is actually a real number minus 1, so that's real. So bring these two pieces together, that's now a minus, so it's a minus there. And bring the two i's together. Now I is common to both terms, so take I outside the bracket, and you get cos k theta sine theta plus sine k theta cos theta. Okay, now we've got our real part here and our imaginary part over here. And the last big step really, I suppose, is to recognize this formula from the tables. Cos A cos B minus sine A sine B is in your tables under the trigonometric identities. Same here, cos A sine B plus sine A cos B. If you look up those formulas, you'll see the answer is simply, in this case, the cos of A plus B. And over here, you'll see the same, the answer is the sine of A plus B. And then what you can do is you can take out what's common. I mean, there's a theta in each term here. Take the theta outside, you're left with k plus 1. And take the theta out here, you're also left with k plus 1. And if you look at what you've just got there, that happens to be the right-hand side that we were trying to prove up here. So we've now proved that the left-hand side that we started off with is now equal to the right-hand side. So what does that tell us? Well, it tells us the proposition k plus 1 is true. We've just proved it to be true. Of course, that's built on a big assumption. The assumption that pk is true, this one right here. So we've got to tie it all together now. So pk plus 1 is true. But that's based on the assumption that the one before it is true, pk. However, we definitely know that p1 is true. We proved that earlier. Which means, according to this, that the one after it is true, which is p2, etc. And it goes on like that. So the two things together means that it's true for all values of n. And that's what we say at the end to get full marks. You have to say that the proposition n is true for all, this little symbol means for all values of, it's an upside down capital A kind of. So it's Pn is true for all values of n, where n is a natural number, which is what we set out to prove at the very start. And that's the Moivre's theorem proved by induction.